What happens when you pass an electric current through a wire? The most common observation that we all have is when we turn on a switch to any electrical appliance, it gets heated up after some time. So that when you pass electricity through a wire, it gets heated up is known as the heating effect of electric current. In chemistry, you might be familiar with an electrolytic solution. When you pass electricity through the electrolyte, chemical reactions takes place. That is known as the chemical effect of electrical energy. And the third one, when you pass an electric current through a wire, a magnetic field is generated around it. That is known as the magnetic effect of electric current. In this video, we are going to talk about the magnetic effect of the electric current. So, welcome to the session and let us start. The magnetic effect of electric current was first observed by a science teacher named Ørsted. And that is why you must have seen or heard this. The experiment that he performed is known as the Ørsted's experiment. What was that experiment? Let us go into that now. There is a basic electrical circuit which has wire and a cell connected with a switch like this. Now, this is the positive terminal, this is the negative terminal of the cell. When you turn the switch on, the current starts flowing from positive to negative. Right? This is the direction of electric current. Now, what if I place a magnetic compass near this wire in such a way that if I turn this switch off, that means the current will stop flowing through it. When I turn the switch off, that means the current will stop flowing through the circuit. Initially, the direction of the magnetic needle in the compass, let us say, is parallel to the wire in this way. In this magnetic compass, let us say initially the wire and the magnetic needle are parallel. Now when I turn the switch on, when the electric current starts flowing through it, in this way, what do we observe? We see that there is a deflection in the magnetic needle. That means the needle changes its position and is like this. Initially, when the current was not flowing through it, the needle and the wire were kept parallel to each other. And when you start the switch, that means when the current starts flowing through the circuit, the needle deflects. Now, you know this, right? When does a magnet gets deflected? Simple, when there is another magnet near it. So, in the circuit, where do you see a magnet? There is no other magnet, right? That means the wire carrying electric current must be producing the magnetic field, and that magnetic field is affecting the magnetic needle in the compass, right? That means there is only one way to explain this. That is that the wire that is carrying the electric current must be producing the magnetic field around it, and that magnetic field is affecting the magnetic needle kept in the compass. This is known as the Ørsted's experiment. Now there are a few things to keep in mind. First of all, the magnetic field that is generated around the current carrying conductor is in circular loops or in circular rings. Okay, so to demonstrate that, let us say that there is a wire. Let us say that there is a cylindrical wire like this. Let me show the direction of current in this way. This is the direction of current. Okay, the magnetic field around the current carrying conductor will be produced in a circular manner in this way. It will be produced like this. It will be in a circular pattern and it will be produced in this way. Okay, you must also be seeing that I am showing an arrow at the end of the loop. Now how to decide that arrow and why am I showing that arrow? For that, we need to understand the right hand thumb rule. For that, we need to understand the right hand thumb rule. Because if you want to decide the direction of the magnetic field lines, you need to understand this. For understanding the right hand thumb rule, you need to imagine that you are holding a piece of wire, conducting wire in your hand. Okay, do not hold a wire with your bare hands like this. Okay, this is just for representation. Now, let us say that the direction of electric current is towards the tip, in this way, in the upward direction. When you hold a wire in your right hand like this, where the thumb points in the direction of electric current, and when you curl your fingers inwards like this, when you hold the pen and when you curl the fingers like this, then the direction of the fingers curling shows the direction of magnetic field lines. The thumb pointing in the direction of current, the direction of fingers curling in shows the direction of magnetic field lines. Now coming back, a few more things to remember. As you go away from the conductor, that means as you move away from the conductor, you will see that the magnetic intensity of the field lines will be reduced. As you move away from the current carrying conductor, the magnetic intensity of those field lines will reduce. So we can say that the magnetic intensity that is produced is inversely proportional to the distance. As we move away, the magnetic intensity will decrease. One more thing, magnetic intensity is directly proportional to the amount of electric current that is flowing through it. So if you increase the amount of current, the magnetic intensity will also increase. So this was it about the magnetic effect of the electric current. If you have understood, then do not forget to like the video. If you are attending the session for the first time, subscribe to the channel. I'll see you in the next one.